Hi, my name is Christopher Gia, and I'm one of the co-authors of Depth Prediction for Direct Visual Odometry. And today I'll be walking you through this presentation. So before getting into the details of our proposed method, we're going to briefly touch upon visual odometry as a topic and some of the prior works. So what is visual odometry? It's a task that concerns itself with estimating an agent's ego motion over several time steps with one or multiple cameras. So in the case of one camera, it's called monocular visual odometry. And unlike SLAM systems, which have a priority of generating a globally consistent map, in odometry, we're more focused on incremental estimation, and we do this through local optimization. So when evaluating our proposed method, we chose to do it on the Kitty Vision Odometry benchmark, which consists of 22 total sequences, and we provide results for the 11 training sequences. With regards to evaluation metrics, we choose to evaluate using the absolute trajectory error and the relative pose error, which are defined by the equations below for a single time step, where P1 through Pn is our estimated trajectory and Q1 through Q1 is our ground truth trajectory. Okay, so looking over at some of the prior works, they generally come in two flavors, the direct and indirect methods. So in the indirect formulation, these methods require a pre-processing step in the form of feature extraction before doing the local optimization. And they focus on optimizing a geometric error. So some examples of this consist of orb slam or methods in conjunction with dense optical flow. In the case of direct formulation, we completely skip this pre-processing and feature extraction phase. Instead, we optimize a photometric error of key points selected directly on the image frame. And this is what is exhibited in direct sparse odometry. So digging a little bit more into direct visual odometry, there have been various extensions that have been made to the original DSO framework, such as stereo DSO, which has been introduced to support stereo setups, DVSO, and then ours. So what are the main challenges that we aim to approach here? The first one is maintaining consistent and accurate scale throughout the duration of a sequence. The second one is to provide robustness with respect to illumination changes between frames, and also to provide robustness against irregular motion states such as strong in-place rotations. Okay, so what is CNN-DVO? So we enhance the direct sparse odometry framework by supplying priors in the form of depth maps. These depth maps are generated from each frame by a deep CNN, which is trained in an unsupervised fashion. We leverage these depth maps for various system subtasks, including initialization, tracking, and marginalization. This is illustrated in the system architecture diagram by the purple box and arrows. Each new frame is processed by the CNN depth predictor, and the corresponding depth maps are used to initialize the depth filter before coarse pose estimation. And if the frame is selected as a keyframe, meaning that a sufficient number of tracking points has been generated for it, and a sufficient coarse pose estimate has been made for it, then the depth priors will also be used for the reprojection of tracking points onto the current image frame to compute our residuals. And these residuals are then used for the local bundle adjustment optimization. So let's get a little bit more into the CNN-DVO front end. So the first proposal we make is an updated point selection strategy, which extends the original point sampling method from DSO. So why do we do this? The original point sampler selects tracking points based on the local image gradient and prioritizes sampling points in high gradient regions, as these points contribute most to the second order optimization. However, in some cases, such as the frame in the bottom right image, this leads to a clustering of points. And such clusters may expose the local optimization framework to corruption under strong rotational motion, where most of the selected tracking points are not visible in a frame several time steps later. So to remedy this, we propose to take a more even sample of tracking points while still prioritizing points in high gradient regions. So after generating the initial tracking points using the DSO sampler, we slide varying size kernels across the image to dynamically upsample points in sparse regions and downsample points in dense regions. During this process, we still prioritize high gradient pixel locations by computing a histogram of gradients within each kernel window. Then we upsample points at pixel locations with the highest gradients. And conversely, in dense regions, we downsample tracking points that occupy lower gradient pixel locations. A little more on the front end. As we previously mentioned, the depth priors are used for initializing the depth filter before coarse pose estimation, and also for the reprojection of tracking points near their local minimum, speeding up the convergence of the second order optimizer. How the estimated camera pose will be used to refine the predicted depths will be explained later. We also incorporate an inverse depth variance propagation, which defines the bounds of the search along the epipolar line, which is displayed in the upper right figure. Noisy depth estimates result in high variance, and in addition, we include an observational variance term that accounts for when the local image gradient is in the direction of the camera motion. Lastly, with depths available for all of our key points, we're able to estimate the 3D coordinates and use them directly as SE3 constraints for offline loop closure, as opposed to the scale-ambiguous Sim3 counterpart. A little bit on the back end. We have our marginalization framework, which aims to accomplish 3 tasks. One is to solve for the camera poses by using the Schur complement of our Hessian matrix. 2 is to eliminate outlier map points. And 3 is to remove redundant keyframes. As our pose is solved for through several iterations of the Gauss-Newton optimization, we use the estimated pose to refine our initial predicted depths until both our pose and our depth have converged. So here we highlight our results on sequence 5 and sequence 9 of the kitty odometry benchmark. Sequence 5 features scenarios where the vehicle loops past previously driven by areas. We see the effect of loop closure in this case, where our method and LDSO, which features loop closure, have similar performance, and both outperform DSO and stereo DSO. In sequence 9, the repetitive rotations pose a challenge to DSO and LDSO, while stereo DSO is able to handle these rotational states, and our CNN-DVO provides strong performance as well. Note that all of our competitors have undergone Sim3 alignment. In our ablation study, we show the effect of our method without depth priors, with loop closure, and without pose prior for initialization. And we find that the effect of pose prior for initialization is almost negligible when using depth priors. Here we've just included some sample tracking sequences, sequence 3, 5, 19 from the kitty odometry benchmark, a sample mapping result in the upper right corner, which includes our selected feature points, and on the bottom right, we illustrate the error of our depth prediction versus distance. So as we can see, points that are further away from our camera tend to have noisier predictions. So here we include some mapping results of ours, LDSO, SDSO, and DSO. So you can note the apparent scale drift in the estimations from our DVO counterparts. And the use of depth priors enables our CNN-DVO system to both maintain scale and accuracy over long tracking sequences. In conclusion, we present a real-time monocular direct visual odometry system that leverages depth priors to jointly optimize for all model parameters. We do this by integrating depth priors into all major system components, such as initialization, tracking, and marginalization. And we use the depth priors to provide useful optimization constraints. We also introduce a new point selection strategy that is robust to challenging motion states, such as in-place rotations. And we show that our method provides state-of-the-art results on the kitty odometry benchmark. Our future work includes extending the current optimization framework for self-supervised fine-tuning of the CNN depth predictor by leveraging the newly optimized sparse depths. And this will enable our system to adapt to new and interesting domains. Thank you.